hablando de, I'm gonna continue talking about puedo hablar español, ¿no? En este momento. So, voy a seguir hablando de las estructuras finas y ayer consideramos este problema, ¿sí? Bueno, dos versiones. Una con las condiciones de Neumann. Aquí en estos dos lados de este rectángulo. Y otro de Dirichlet, ¿sí? Y vimos que mientras mientras H es is the thickness of this strip, right? Mientras H, when H goes to 0, we have two different limits. So the solutions to the problem are minus Laplacian equals f, where f is a function of x1 only for simplicity. So I was the interval from minus 1/2 to 1/2. And so we're looking for u, the solution u is in L2 on the rectangle. That u, in this case, in the case of Neumann, it converges strongly. In fact, I didn't show the strong convergence, but it's immediate from the weak convergence in H1. So it was kind of implicit. So this converges strongly in L2 on this domain omega h. So I call this omega h. So omega h is this domain, right? Converges strongly to u, which solves the problem minus u. So u does not depend on x2, and u solves this problem. And in the case of the Dirichlet problem, goes to 0 strongly in L2, but when we scale it, and we discussed why we should choose this scaling in order to have a non-trivial limit, then this converges strongly in L2 to the function w that solves this problem. So w is a function of x1 and x2, and it satisfies the boundary conditions, the Dirichlet boundary conditions at these two sites, right, where we have the Dirichlet condition at the beginning. Okay, so I actually didn't have a chance to give you an exercise, but maybe you can think about it today, and well, for the rest of the course, is to study using the same approach as we discussed yesterday. Consider the problems where you have the Neumann conditions on these sides, right? And so we have minus Laplacian equals f. F is again still a function of x1 for simplicity. So, and we have either the Dirichlet conditions here or the Neumann conditions. Right? Okay, so what is the behavior of the solutions to these problems? I'll write that the question is really to understand the asymptotics of the solution as h goes to 0. So sometimes, as you could see, sometimes you need to scale in order to get the non-trivial asymptotics. So the answer here that UH goes to 0 in L2 would not be interesting. It's a straightforward answer. What we then need to do is scale and see what basically what the leading order term of the asymptotics would be. So this result, for example, means that UH behaves as h goes to 0 behaves as h squared w right, like this, and here it means that UH behaves as this function u of x1. Okay, so now with this I will move on to the problem of elasticity related to sort of the next level of the same type of question, which is considering a vector problem, a system of equations, right? So Shane yesterday talked quite a lot about systems, the systems that appear in elasticity theory. So how many people are familiar with these notions of elasticity theory and equations of linear elasticity, by the way? No? Okay, maybe maybe we should talk a little bit about where these equations come from, right? So okay, so I'll just announce then what we're aiming at eventually, and I guess well, this part is already clear what we're thinking about. We're thinking about some differential equations on domains that have some dimension going to 0, right? By the way, there is a massive catalog of problems that have been looked at, and this is not exhaustive yet. This topic is not closed yet. About studying problems where some kind of length parameter goes to 0, right? So actually, one class of such problems will be discussed. I was hoping to talk about it a bit today. The problems that appear in the subject of homogenization. So when you have a periodic medium, like in Shane's talk yesterday, but you are looking at the asymptotic behavior of solutions to the equations when the parameter that represents the period of the medium goes to 0. So in Shane's cartoons yesterday, the period was 1. So he was looking at the propagation of waves through a medium with period 1. But then you can say, okay, so what if I have some kind of object with maybe some sources of waves, right? So some kind of mechanism of producing waves represented by this function f, and these sources are distributed somewhere on an area of fixed size, but the medium through which these waves propagate is periodic with very small period, and then the problem, you move into the realm of studying asymptotically the behavior of solutions when this parameter, the geometric parameter, the length parameter, in fact a ratio of two lengths, the length of the period, the size of the period, and the size of the domain on which the sources are sitting that produce these waves. when this ratio goes to 0. So it's a class of problems where, I mean, really you can spend several years at least just getting to grips with the subject. So here also we have this h is well, it's a parameter that represents, it's a length parameter, a parameter that represents a ratio of two lengths, right? In a real problem. Of course, in mathematics, well, and in physics too, you want to kind of get rid of all the dimensional parameters in the process of your analysis, right? So divide meters by meters, seconds by seconds, and get get rid of all dimensional quantities and end up with some non-dimensional quantities with respect to which you can then analyze the problem. So here, such a quantity h, so here h would be in a real problem it would be the ratio between the thickness measured in meters to the length measured in meters also. So, and we can rewrite the physical problem in this form where we simply fix the length of this to be 1. It's not a length anymore, really, it's just a number 1, the size of this, the length of this rod, and the thickness becomes h. So there are many problems like this. So you could just take any context, some equations of fluid mechanics, non-linear, even like Navier-Stokes equations, in a domain that has some thinning parts. For example, there is flow through a very thin domain, and then because it is thin, and the overall you want the solution to still satisfy the equations, Navier-Stokes equations. There is something going on. There is some kind of asymptotic behavior that physically means that the fluid forces to behave in a certain is forced to behave in a certain way, right? And the goal of the asymptotic analysis is to elucidate that behavior. Now we are almost always unlikely to write an explicit formula, just a formula for the solution. So that's why we are in the first place aiming at some asymptotic analysis, just to understand what the solution looks like in the, to the leading order, so that when I subtract, say, this function from the solution, I get something small. So that's where the word thin rods comes from. It tells you that you are gonna be doing some asymptotics. Now this elasticity is something that Shane mentioned yesterday, but maybe I can give a short introduction. So, well, he essentially wrote the equations of elasticity, the equations of linearized elasticity. So there is even here in IIMAS there is a group of people who have studied problems of nonlinear elasticity, where the mathematical objects are a little bit different, but as what was shown not so long ago, actually the equations of nonlinear elasticity, well, the equations of linear elasticity can be mathematically rigorously derived from equations of nonlinear elasticity. And by the way, that also involves asymptotic analysis. So what is linear elasticity? Linear elasticity is a limit of equations of nonlinear elasticity when you have finite deformations. So in nonlinear elasticity, you study how elastic bodies respond to finite deformation. So if you apply boundary conditions that deform the body a lot, and but often, especially in wave propagation, like in acoustics, we're interested in deformations that are not very large, right? And whose in principle, you need to assume that the deformations are not large and their gradients are not large. So it's actually the gradients of the deformation also that are important for whether to use equations of nonlinear elasticity or equations of linear elasticity. So assuming that the amplitudes of the deformations and their gradients are not very large, then you can kind of linearize. What is linearization? It's asymptotic analysis, right? You write Taylor expansion around some steady state, and there you are. So So in that sense, from that perspective, equations of linear elasticity are some steady-state equations. Well, some linearized version of nonlinear equations of nonlinear elasticity. But because they're so important in wave propagation, because you have such a variety of physical phenomena and mathematical effects associated with just equations of linear elasticity, it's worth studying them. It's more than worth studying them in their own right, and not say, oh, I'm gonna be as general as possible, and I'm not gonna leave the world of nonlinear elasticity. Then probably you won't be able to do much, right? So it's an interplay between being able to do something and addressing a real problem. So that's when the people kind of decide, okay, maybe I can do equations of linear elasticity because the physical problem I'm solving satisfies those conditions under which I can do this steady state, linearization first, and then you end up with these equations that I think Shane wrote in this form. J, okay, so KL, right? KL, and he had rho here. U. So he wrote the second Newton's law, I think. So rho here. Well, his rho was in general anisotropic, and so this is some S. So this is ISUS, something like this, right? So if rho, you can assume for simplicity that rho is a scalar, then this is just rho times u, the component ui of the displacement. So what is u? U is that displacement, the displacement of the points of the medium. So you can think of some elastic body, well, elastic in the physical sense, so some kind of body that supports what you intuitively think of elastic deformations, like a piece of rubber or something, or anything that this building is built of, right? We have waves propagating everywhere. So there is this body omega, and then U actually represents the amplitude of the points in this body, the displacements of the points of this body, right? So if this is under the action of this wave that is shaking omega, it deforms slightly. Then this x is moved to some point phi of x, right? And phi is referred to as the deformation, this mapping, and so u will be actually scaled. This needs to be made rigorous mathematically. Difference between phi of x, so u of x, the scaled difference between phi of x and x. And so the actual deformation is assumed to be small. So the actual deformation phi of x minus x is going to be small. So it behaves like some small quantity. Let's call it just epsilon. Some non-dimensional small quantity times u. So because we have scaled it, you see it's actually not dissimilar to what we did here. So when we scale it, when we divide phi of x minus x by epsilon, we get something finite. And that's exactly the quantity that satisfies this equation. So here u is not small, of course, because you have this, right? And then you kind of forget about this finite elasticity business, where you deal with phi and start dealing with u. Now you can derive these equations, as I said, from equations of nonlinear elasticity, but you can also bypass that and kind of argue in a argue from the point of a physical intuition, where you will use all this assumption importantly, one way or another, and arrive at these equations as well. And this is what you often see in textbooks as well, where actually more often than not, these equations are derived directly. So you simply say, what does this mean? This means that, what is this equation? This equation is a combination of two things. So it's a combination of the conservation of momentum equation. Oh, I need to U double dot here, right? So and maybe I'll put right. So what's the best way to do this? If I just assume that I have some sources here in addition, some function f again representing sources, and well, so I can still write it in this form. So this is the second Newton's law, right? Well, I assume that rho is scalar. Ui plus fi. So what is this? This is, in other words, this is divergence of some matrix. So this as you can see, this divergence is taken row-wise. So you take a matrix sigma and you take divergences of all rows, of each row, and you get a vector. And this is u double dot plus f. So this is a vector equation now. Well, maybe I shouldn't use this as a mathematician. You know, in the engineers often use this notation. I find it unnecessary, right? So this is to underline the fact that this is a matrix, this is a vector, and this is a vector. Right? So this equation is valid, is derived on the basis of balance of forces, right, in the medium. And so as such, it's applicable to elasticity, fluid mechanics, any continuous medium. It's some version of it is also applicable to electromagnetism. Before you say what sigma is, you don't care. It's just an equation of a balance of forces in a continuous medium. So the word elasticity comes in when you write what sigma is, in terms of the function that, in terms of the field U that solves this equation. So this is the balance of momentum, right? Equation. Balance of momenta, right? And then sigma, when you write what sigma is as a function of U, then this is referred to as constitutive law. Then you combine the two and you get an equation on U. And here there is quite a lot of freedom still, of course. I mean, all I said is that I'm gonna be looking for sigma that is a function of U, and possibly its gradients, actually. I can even say it's a function of U, its gradient, its second gradient, if I like. You know, I could take fairly general dependencies, non-local dependencies. It could be some integral of U. So since this dependence is very general, I could just write sigma of U, and that's it. And then depending on the context, and well, what I think is true about the medium I'm looking at, I start being more specific about this dependence, and then it becomes equations of fluid mechanics, equations of elasticity, electromagnetism, and so on, right? So for example, and even within elasticity, you have many options. You could consider, for example, well, typically in elasticity people assume that sigma depends only on the gradient of U and nothing else. Um, but you don't have to make such assumption. It can be, the dependence can be more general, right? But this is typical. So typically in elasticity, sigma is a function of the gradient of u only. People who don't just study this case refer to this case as hyperelasticity. That's well, no, not hyper. No, this is, well, they attached the word something like standard elasticity to it. Hyperelasticity is yet something more specific than this. So when sigma is actually written in an even more explicit form in terms of the gradient of u. Right? So, but in linearized elasticity, we assume that this dependence is linear, right? So simply in linearized elasticity, and I say linearized, and some people say just linear. We say that sigma is just some tensor times the gradient of u, and that's what's written here, right? So now you kind of, you know where this comes from, and you just need to get used to these equations written in various forms, either in this form or in this form using indices, right? So sometimes one is convenient, sometimes the other, right? So, but this is a system. So in general, in 3 dimensions, this is a system of 3 equations with 3 unknowns. Okay, so and it's a partial differential equation, and well, with time it makes it even more complicated than if you considered steady states, right? If u did not depend on t, and then you say, well, maybe I can look at some polarizations in this medium, and rather than study this complicated object, try to decompose the u into some components, each of which satisfies its own equation. And this is what Shane introduced so nicely yesterday. Some way of decomposing solutions, right? So you can decompose so if C satisfies some additional assumptions, namely it does not depend on the point in the medium, because of course in general C depends on X. At each point the elastic body behaves in a certain way. Then you move from one point to another, the properties change, right? So for example, in a composite, in a periodic medium where you have inclusions of I don't know, rubber in some plastic or metal, you are going to have one kind of properties in one material and then another kind of properties in the other material, right? So overall the medium becomes inhomogeneous, and in general even anisotropic, right? But at each point it's approximately homogeneous, and then you decide whether you are interested in the properties of the medium at a given point and not very far, where you can assume that the medium is approximately homogeneous, or whether you would like to study the whole thing where you do see this variation of C, and then the most arbitrary variation is maybe too general, you can't say much, you need to make assumptions like it's periodic or something so that you can carry out some analysis. But if it does not depend on the point, if it's a homogeneous, imagine, it's a bit idealized of course, but imagine just a homogeneous elastic medium with whose properties do not depend on the direction, so isotropic. Then C only depends on 2 parameters, and it's an approximation of some physical situations where the body is approximately homogeneous and isotropic. But for us mathematicians, at this point, we detach ourselves from the physical situation and say, well, C just depends on 2 parameters in the way that was described yesterday, right? So where it was lambda and mu, the so-called Lemma parameters, and C is just, maybe shouldn't. Well, I can just as a reminder, I can write it. So this isCijkl is lambda Cij delta ij delta kl plus mu delta ik delta jl plus delta il delta jk, right? So this is the form. This is yet another restriction that we make assumption maybe to have a first go at the problem, and it's already fairly complicated. That the medium is homogeneous, lambda and mu do not depend on x, and isotropic, that it actually has this form, the tensor. And then you start, as a mathematician, you start with something what you think is the simplest, but complicated enough, and then you start increasing the difficulty, right? You maybe start assuming that lambda and mu start depending on x, then that it doesn't have exactly this form. Maybe it's anisotropic. Are you going to talk about anisotropic? Periodic, yeah. Okay. But then also one level of simplifying. So mathematically, we want to simplify things as far as possible, but not too far, right? A kind of one more degree of simplification that allows us to still get something interesting is polarizations, and this is what Shane was talking about yesterday. And it kind of represents, it's a polarization in relation to the wave motion. There are other ways to decompose this equation. For example, you can just assume that the displacements in the medium, I don't think about the wave motion for a second. Think that this is zero. I look at the equilibrium equation. So I want to go back to kind of setting that we started with here yesterday. So imagine that there is no wave motion, there is just the medium is in some kind of equilibrium. So either time is fixed or it's some kind of steady state, limit in steady state, right? Then you can then look at the situations when the motion is only in certain directions. The displacements are only in certain directions. So, and that's going to be, in certain directions with respect to the chosen coordinate system. So you have chosen some coordinate system in your problem. Say that you have the board and the coordinate going in the orthogonal direction, and then you can say, okay, how are the points of the body displaced? If they are only displaced in that direction, like this is called antiplane shear, right? And this equation, this diffusion equation, is exactly the same for antiplane shear. So it serves both diffusion, steady state diffusion, and antiplane shear when the points of the medium are displaced like that. So the properties are going to be almost identical, the conclusions of the analysis that we carried out yesterday, and for when I just replace diffusion by antiplane shear. Or you can, but it's still a scalar equation then, right? Or it can be a vector equation. The simplest version of a vector equation that you get from here, but not as complicated as 3D, is two-dimensional elasticity, right? So which describes the displacements in the plane of the board. So you assume that the displacements don't depend on the variable orthogonal to the board. So there are only two components. U1 and U2. If x1 and x2 are the coordinates in the board, and then you have a system of two equations. With two unknowns. Right. So this is what I kind of expect or anticipate one thinks about when I write this. So we take this geometric picture, but move on from a scalar equation to a system of two equations with two unknowns. And this is where the method that we used yesterday becomes well, it's still as a method, as an idea, it's still valid, but the analysis is going to be totally different, because you have now two components, U1 and U2, and you have to derive all those. You have to work out to understand how you scale each of them. So here there was only one thing to understand: this scalar quantity UH, which represented the temperature in the diffusion problem, or in the antiplane shear problem, it would represent the displacements in displacement in that direction. But we have two now, U1 and U2, and they are going to be scaled naturally in different ways, depending on whether they go whether they represent displacements along the rod or across the rod, right? So if I think of an elastic rod, thin, then, and when you think of displacements in the direction of the rod, you need a bit more force, right? Than when you try to pull this up like this, or actually even the two simplest possible boundary conditions you can imagine, they lead to totally different behaviors. So pulling like this, the component of the displacement that is going along the rod plays the major role, and it's kind of hard to pull a rod like this. But if you do it like this, push it together, so just the opposite direction of the boundary displacement, then it's easier to do. Then it buckles or bends, right? Right? So it behaves like this. It's much easier. It's much easier to do this. Look, I apply almost no force than to try and pull this. So here I get huge displacements, right? Already. Actually, this tells you that to study this, you definitely need finite elasticity. You cannot use equations of linear elasticity. But maybe if it does this, it's still quite easy, right? But doesn't displace too much, I can use these equations. So this is acoustics, so vibrations like this. And this is what we are often interested in, not this, right? But definitely when I try to do this, that requires much more force anyway, to displace by the same amount. So that means that the two combination, well, there are two linearly independent sort of displacements, U1 and U2, two components. And it depends that it means that the different linear combinations of them, the ones that correspond to the direction along the rod, here it's just U1. And those that correspond to the direction across the rod, U2, they need to be scaled in different ways. They will be scaled in different ways. That's what we anticipate. And remember, the first step in our analysis was to get the energy estimates, to write to that Poincaré type inequality, to get the compactness estimates and start extracting subsequences and so on. So probably in order to understand, well, almost inevitably, in order to understand this problem now in a rod, we will need to write versions of such a Poincaré inequality that take care of the displacements along the rod and across the rod in different ways. So they're going to be kind of anisotropic. Here, the anisotropy, even for an isotropic medium, the anisotropy in the problem is introduced by the geometry. So because of what I just said, it behaves in different ways in different directions. So, well, what time is it? Okay, so so what I was gonna say now is actually contained in the first few pages of that first paper. So it's a very accessible paper, I think. You can, I encourage you to look at it. You can, well, hopefully, when you read it, you will remember what I was saying now, and it will be a good reminder, and at the same time, a more advanced a more advanced introduction. So when they say thin nets, they mean thin. They actually consider thin strips. So it's equations of 2D elasticity. So nets is just the word for the net is the word that they use for rods when for the two-dimensional situation. So what is the geometry then? The geometry is like this, but now with equations of elasticity set on them, on objects like this, and something I haven't discussed, even though I could. Yesterday there wasn't enough time. Well, there are too many things to talk about. Is what happens when I have a structure a bit more complicated than this, right? A net. So this is not a net yet. This is just a strip, one strip. The reason why we start with it, because it's the simplest object, yet interesting enough. But if I look at something like this, right? So several strips joined together, and then you may have something here as well. You know, you can imagine anything. So it seems that, well, somehow what we already understood, at least for the diffusion equation. Again, let's think for a second about the diffusion equation. So scalar situation. What we have already said is going to apply far from these regions, right? So imagine that these parts are very long. The distance between the vertices is large compared to the thickness. It's all relative, right? So if we have a net of very thin objects, what does it mean? It means that they're thin in relation to the distance between where they're pinned, right? So then what we said, what we derived, the behavior that we obtained, should be applicable here in these regions. But we have done nothing yet to account for what happens here. And this is something that was worth looking at even in the diffusion equation. If you like, that's maybe you can think of it as an exercise as well, to try at least to think about it. Maybe you won't get a definitive answer, namely what conditions. So in the limit, as h goes to 0, well, imagine that all of these thicknesses relative to some fixed length, like the typical distance between the vertices, is very small. Then the limiting object should be something like this, right? Well, now I need to try and copy it. So geometrically, it's something like this. Right? And we have understood quite well that in the case of the, say, conditions, Neumann conditions here, we're going to end up with the diffusion, one-dimensional diffusion on each of these links. But okay, but that's not enough to set up the problem, right? So if you solve the diffusion equation here, the diffusion equation, well, each link has its own diffusion equation. You need to take each interval and solve the diffusion equation. You get, so when you solve the diffusion equation on minus u double prime equals f on one edge, you're gonna have two independent constants, right? As two arbitrary constants, because this is an ordinary differential equation. Right? Everyone is familiar with the theory of ODEs? Well, linear ODEs with constant coefficients. So it's second order, you need two constants. That represents the way in which the solution is written as a linear combination of fundamental solutions. Well, here it's a little bit more complicated because there is a right-hand side. Imagine that it's 0, even. So already even any solution of this is a linear combination of two fixed solutions, but an arbitrary linear combination. So you need to determine two constants. And then you have two new constants here, two new constants here. So how many constants do you have? Already on this picture you have as many as twice times the number of edges. So if so you need some extra conditions to determine your function. Where do these conditions come from? Well, they come from the same place where the conditions on the function that solved the limit equation for this problem came from, right? So we started with the problem with certain conditions here and ended up with this problem. U at -1/2 is U at 1/2 equals 0. Well, these conditions came from here. Well, here they will also naturally come from somewhere. From where? From the endpoints, right? So we need to investigate what happens, what we get here, and that means we need to understand asymptotically how solutions behave in these regions. And this is something we haven't done. Okay? So there will be something here, there will be there will be diffusion flow, there will be diffusion along these channels, and then the flow, well, the diffusion against along each of these channels will be tied together in some manner to satisfy, to solve the whole problem. This is the kind of coupling between the behavior on each individual strip, and we have said nothing about this coupling, what it means, and what conditions it results in here. Well, maybe I will give you the answer here. What the answer is. So basically, you need to solve the equation minus u Laplacian equals, minus u double prime equals 0 on each edge. If there is an f, well, you know how to solve that as well. So it's going to be a linear combination of two solutions of this problem, plus some fixed solution, which you can actually write explicitly. You can write explicitly everything here, pretty much, of this problem, right? So whatever, you solve it here. Here is some f2, and so on all edges. And then you impose the conditions of, and I'm going to refer to this as u1. Sorry about the clash of notation. This does not represent the first component. There is only one component. It's a scalar function. So what I'm referring to is the restriction of this function to the corresponding edge. So you are going to have 3 here, 4, 5, and so on. Just number them somehow. And so you have these functions u1, u2, and so on each edge. And the conditions are going to be that these functions have to arrive at each vertex with the same value. So the overall function, when you piece them together and you write the whole function on the graph, is continuous throughout. And that the sums of the derivatives, so u is continuous, and the sums of the derivatives that we obtain when we approach each vertex along each of the edges that meet at that vertex. So, for example, if here you have 6, 7, then it's going to be the sum of the derivatives. So here it's going to be u1 prime plus u2 prime plus u6 prime plus u7 prime. And you calculate these derivatives all in one direction, say towards the vertex. Then this should be 0 as well. So you may have come across this in physics as the Kirchhoff rule for electric circuits. So you can just think about the flow of current, right? So this means that the sum of the currents is the net current is 0. So what flows in should flow out, and this means that there is a specific potential at that point. You cannot have. I mean, if you measure, if you walk, the people measuring the potential in relative to Earth, right? Walking along each of these each of these paths, each of these edges will arrive with the same potential at that point. Right? It's this condition. So, and then you have this. So over all I that meet I for the edges that meet at a given edges that meet at the vertex. So it's written for each. These conditions can be written for each vertex, right? If you count the number of conditions now against the number of unknowns, right? So here, if this is where it ends, if you don't have more edges, then you can put some. You can set some conditions here, like that, like Dirichlet, if you like, or Neumann in the exercise that I gave you. By the way, for the context of electric currents, you know what the Dirichlet and Neumann are gonna mean, also, right? So no potential or no current. So U equals 0 means these are grounded, right? And U prime equals 0 means that there is no current at those points. Okay, so when you count the number of conditions against the number of unknowns, you will see those constants that you obtain by writing the solutions to these equations in the most general form. Then you will find that those two numbers are equal, and so you have a consistent problem where the number of equations equals the number of unknowns, and you can solve it. You can determine all those constants. That's the solution to the problem. I'm stating that that's the solution. Once you have solved that problem, once you have determined those constants here, that's going to be the limit in the sense that we've described, that strong L2 sense in the rescaled sense, after rescaling, of solutions in this problem. Okay, and you can carry out this mental exercise for each of the cases. Then Dirichlet, then you have Neumann. You can imagine all possible combinations here, right? Maybe for some physical contexts, some of those boundary conditions are not going to be relevant, are not realizable. Then they become a kind of just mathematical exercise. But I think all of those situations are realizable in one or other physical situation. Okay, so, but you see, this is just the scalar problem. Now, in that paper, there is a similar picture, but now instead of the equation minus Laplacian u equals f on this domain. Maybe I close them here, since I decided to put to nail these points down somehow. So this is the domain omega h, right? So u is in L2 on omega h, u which depends on h. So, and what we have discussed here is the result of this asymptotic analysis, right? So, but in that work, the step is taken, well, and it's quite a leap, as I said, because of this, need to deal with the mathematical challenge of a version of the Poincare inequality to start with, and then there are, you need to see what it all means in the end. The kind of analysis that we did, but for each of the components, U1 and U2, when you consider, instead of the diffusion equation, the equations of linearized elasticity on a net, like on an elastic body, I suppose here it will mean that physically it represents an arrangement of plates that are fairly long like this and are geometrically invariant in the direction orthogonal to the board. and there is no displacement in that direction. So all the mathematical analysis is going to be on the cross section. Okay. So I'll write. Shall we have a break now? Yeah. Shall we have a break, and then I'll write down what the what the problem is more explicitly for elasticity, and what the answer is, similar to the way the answer was written here, right? Okay. So maybe we resume in 10 minutes. Yeah. Bit careless, given the effort that he made yesterday about writing the equations correctly. I put the wrong sign in the wave equation. So of course, well, the wave equation is this, right? That's the way he wrote it. And I decided to write it with the u double prime in the right hand side, but put it with a plus again. So this should be minus, right? if I decided to write in this form. I mean, I can't really do much about the sign because u is meant to be non-negative. Oh well, u here and here, sigma depends on, you should have the same sign, and then, well, unless I said that rho was negative, that would be my that would be my way out. But I won't do that. Okay, so so this is the wave equation, right? So, but why? You know why people prefer to write well, one reason why people prefer to write minus here is because when you are in a steady state, u is constant in time. Then you get minus. So that's why people often write like this. But the second reason is because, well, it's a related reason. Is that like this, when you write the kind of energy formulation of this problem, or weak formulation, as we called it yesterday, right? When you say that u sigma dot gradient of u equals fu, f or phi. Well, phi is not this, so psi, let's call it psi. Phi was the deformation. So psi, for all psi, then you get rid of that minus, right? It looks, you don't need to write any signs. So that's why you write minus in the first place. Well, there are several, I mean, you can express this in the same reason in different ways. You can also say that when you write it like this, then you have, you know, when you multiply by u and integrate by parts, this is then this can be written as a law of conservation of energy. But if you had plus here, then it would look very strange afterwards when you write the expression for the energy. One of your energies would be negative. Okay, but I hope everyone kind of is clear about this, and I don't cause any problem for the next lecture by Shane, where he will write the correct version again. Okay, so right, so here is the problem now. So I would like to so Shane called it C, so I will call it C. This tensor of elastic. They're called elastic moduli, or simply, if you don't want to use moduli, you can just refer to them as coefficients. Okay, so Cijkl, and so for the homogeneous and isotropic, or rather I should say isotropic first and then homogeneous. homogeneous Cijkl equals lambda delta ij delta kl plus mu delta il delta jk plus delta ik delta jl. Where lambda and mu are constant, and so the problem, which is a direct analog of this problem, is but well more sophisticated, right? Is to find a solution in well, it can be formulated like this. This is one way of formulating the problem, one of several ways. Likewise, you could formulate this problem in several different ways. Actually, the way that I formulated yesterday is different from the way I'm going to formulate this problem here. But I did mention that you can write the corresponding weak formulation. So the weak formulation here was just recall, right? This was already here yesterday. So u1 1 u1 plus u2 oh sorry, phi. It was called phi. Now maybe, well, phi or psi doesn't matter, whatever letter you prefer. So phi 2 equals integral of f phi for all phi in well, in the you can take smooth functions, set of smooth functions, set of it's actually an appropriate set of smooth functions, right? Appropriate set of smooth functions. You know that this set depends. If you follow yesterday's lecture, then you will see you know that this set depends on the boundary conditions, the set that you take here. But the same problem can be reformulated using the language of, referring to this expression as a bilinear form, and in that case, taking phi from the same class as u. Now, there is no difference in the end, because this function's phi, this set of smooth functions, is chosen in such a way that it is dense in the norm of your space in which you solve this problem, L2, right? It's all about dense subsets in L2. A little bit like in Luis Silva's talk yesterday. So you need to think about unbounded operators with dense domains. The space. Well, not only this set of smooth functions is dense in that space L2, but also when you close it with respect to, so when you close it with respect to the L2 norm, you get L2. That's the density of the domain. When you close it with respect to the energy norm, the norm that is associated with the derivatives of u, like u1 squared plus u2 squared integral, then it's going to coincide with the space in which u lives. That solves that is taken that belongs to the domain of that bilinear form, right? So the bilinear form here is going to be exactly this expression here. And since it's a language of bilinear form, you want to take phi to be in the same class as u, which is the class referred to as the domain of the bilinear form. And since this set is dense with respect to the norm that this bilinear form generates, the energy norm, then the two formulations are equivalent. So I'm going to use this bilinear form type formulation here, just for fun, just to just to demonstrate that you can do things in different ways. So the problem is to, well, this is just one version, right? Maybe I should say, just to make it very close to the setup that we were discussing yesterday, let's consider a rod, just a single rod, no network yet, just a single rod. it's actually, well, it's not a rod, strictly speaking, right? It's a plate that goes into the board, which we study in the polarization, where the displacements in that direction are zero. So you actually end up with the analysis in the cross-section of the displacements in the cross-section, and it becomes what they refer to as a component of a net, which is a strip, which is the cross-section of a plate. Right? So I know it's a bit confusing, but I think the language here matters. Maybe I shouldn't refer to this as a rod because it gives the wrong impression. That that this problem comes from this from a rod, right? But it's not. Okay, so a strip, right? An elastic strip. So with the zero condition here, x1 equals minus 1/2, and well, it can bend, right? It can bend, stretch. So you can think of this as a cantilever, like in Louis Silverstock. So this is what they call cantilever. You have an elastic, like some kind of fairly rigid material. Well, it can be some, I don't know, whatever, a piece of metal, and then it's glued or fixed to something, right? To some base, and then you start deforming it, pulling it in different directions, and or just giving it some displacement and seeing what happens, how it vibrates, or well, move it a little bit and see how the displacements behave if they're not very large. So for each of these problems, you have to kind of focus on the physical setup and decide carefully which set of equations you're going to be using, so that you don't end up studying I don't know, problems where the displacements are not small with equations that are only applicable to the situation when they are small, right? But here we are assuming that we are in those conditions when we can write the equations of linearized elasticity, and so I'm gonna I called it omega h, right? This domain, the same domain as yesterday, and I have this formulation, which would correspond to this in the scalar case, where phi is taken in the same class as u. Phi. So, and here, here comes already an interesting thing. So, you are, at first sight, you feel like doing this, right? Just saying F, which is a force, the density of applied forces, dot the phi for all phi in this class in H1. Sorry, this is omega h squared. So the two component functions, each component lives in H1. Plus, they satisfy this condition. So phi is 0 at this end. But this problem is not the problem that we are going to talk about. And the reason is because this anisotropy, this geometric anisotropy, when the two components of the displacement along the rod and transversally to the rod must have different scalings with respect to h. So remember this example, this kind of example suggests, since you need to use much more force to pull the sheet of paper than to bend it, it means that if you apply the same amount of force, then the displacement in this like in the horizontal direction is going to be by an order of magnitude, well, by an order of magnitude or several orders of magnitude smaller than displacement in the orthogonal direction, in that direction. And that means that well, first of all, the Poincare inequality will need to be written in a different way, with those components scaled differently. But that also means that the original problem, in order to account for this effect, in order to get something reasonable, some reasonable information about the behavior of your elastic medium, you need to scale the forces in different ways as well. You can still consider this problem, no problem, but you will get a different limit. You will get a different answer. Now, what that answer is, honestly, I have not had a chance to look at. Maybe, well, if I sat down for an hour or two, maybe I would work it out. But when preparing the talk, I decided to choose a different scaling, the one that people normally choose when they describe the situation, when they want to describe the, well, I guess very mathematically oriented people would say the most interesting case, right? But I'm not very happy about that. I want to kind of find physical motivation, and my motivation stems from the fact that you get different. You fundamentally you need to use different scalings for the displacements in two different directions, and that means that the forces need to be scaled in a different way. So F1, so F. So instead of this, rather than this, we consider the formulation where the force in the direction along the rod, so this is x1 and this is x2, is much smaller than the force in the direction, well, is much larger actually than the force in the direction x2. So this is the formulation that we're going to study. So this is a kind of new feature compared to the scalar problem. We kind of already at the point of formulating the problem, we need to think about the way we scale the density of the applied forces. And mathematically, it's just gonna be convenient and give you some interesting analysis. If I was a pure mathematician, mathematician who cannot be bothered or doesn't like talking about applications, but just talks about analysis of differential equations, I could just say this is going to give me some interesting analysis, and I'm going to just assume this, full stop, accept it. But try to think about this in this way. So you want to apply the force in the orthogonal direction, in this direction, much smaller than the force in that direction, so that you don't get large displacements when you will be taken out of the realm of linearized elasticity. Actually, if you don't make this assumption, then the approach via linearized elasticity becomes questionable. So if you like, this assumption about the forces is linked to the fact that you are using this equation, this type of energy, with the quadratic dependence on, or with the linear dependence on UH of phi. So E is the same thing as in Cheyne-Stokes, is the symmetrized gradient. So this has got components. This is a matrix. Okay, so but mathematically, this is gonna be convenient in that when I try to make the next step similar to what I did in the scalar case and derive a priori estimates, right? Use some kind of Poincare type inequality and bound this below by something. What I'm going to bound this above by is going to look like the expression that I'm going to get here. But here it's going to be squared, and there it's going to be into power 1. So I will get those cancellations on both sides, and I will get a bound, an appropriate bound on the two components of the displacement, scaled in different ways. Because look, if I write this, if I move this h, if I think of this h as being attached to phi 2 now, then this is going to be, well, so this, so like this, we get a bound of this kind. I should use brackets. You know, the new generation, I know, the new generation doesn't like brackets. But I'm from the old school. I think brackets are necessary there. Otherwise, it's the integral plus that expression. The integral of this plus that expression. So I'll use brackets. So this is bounded by the norm. The norm of, well, I'll write it in detail maybe. Using Cauchy-Schwarz inequality, you can bound it by f1, the integral of f1 squared plus f2 squared, right? So this is all over omega h. And here I'm going to have the integral of phi 1 squared plus h phi 2 squared. And it turns out that this is the kind of expression that I get here when I bound below. So if I didn't have this h here, this bound would not be valid. That I'm still to write. And this is a subtle point here already in the analysis of elasticity problems. That even for the Neumann problem, remember the Neumann problem in the scalar case had the finite Poincare constant. It's the Dirichlet problem that had this Poincare constant, well, the constant C that we had last time, yesterday, was blew up, right? So the Poincare constant, which is in the standard Poincare inequality, is going to be the inverse of that, which is small. Here, something like this happens at the level of looking at different components of displacement. So this is a vector feature. This is a feature of a system of equations. It doesn't happen in the scalar case, and that's what makes the problem mathematically, you know, a level by degree more interesting, right? Oh, it's h squared, of course, here. So okay, so what is this mysterious inequality I'm referring to? So the version of Poincare inequality. Anyone knows what sort of has heard of the name for the kind of inequality that you use in elasticity problems that plays the role of that Poincare inequality? Korn, yeah. So so these Korn inequalities, it's a whole class of inequalities. You can say. I mean, in textbooks you find usually two main versions referred to as the first Korn inequality and the second Korn inequality. But this is just this is just a convention. People like referring to the Korn inequality with the Dirichlet conditions on part of the boundary as the first Korn inequality. It's easier because you can just obtain it by simple integration along the lines. And the second one is it's a trickier one, that is called the second Korn inequality in textbooks. So by the way, there is a good book that is is somehow relevant to this stuff that you may want to look at. It's a book by Olejnik, Shamaev, and Iosifian. I'm not sure how this is spelled. Okay. Yeah. On homogenization. Homogenization of elasticity problems or something like that. You remember the exact title? Something like this. Well, look for these names. It will pop up in Google search. So the first few pages, the first chapter of this book is a nice introduction into these Korn inequalities and their role in the analysis of equations of elasticity. Well, linearized. It's all linear in the book. So, but unless you start talking about thin bodies, strips, nets, like we do, you don't have this anisotropy yet, right? In that U1, the displacement in that direction, the displacement in that direction are going to be scaled in different ways. So there is no dependence on H. In that book, they just started with the body, start with the body, omega, a domain represented by the domain omega, with no parameters of the kind that I started talking about, this morning, when you have one of the lengths much larger than the other. So it's just a general situation, a general domain, fixed domain. Let's consider equations of linearized elasticity and say prove that this problem under some conditions on the data has a unique solution. Maybe you can ask how the solution depends on the data, but no H, no small parameters yet. Here we are already stepping beyond what the first chapter of this book is discussing. Namely, we're introducing a small parameter. And this is where we need a new kind of Korn inequality, which takes into account the geometric nature of the problem. So it just becomes another Korn inequality for us, right? It's not exactly the first Korn inequality or second Korn inequality. It's some kind of version that takes into account these different scalings in different directions. And so now I'm going to write what the inequality is. Okay, it's actually this picture is very nice. It's going to be, as you can imagine, I'm gonna use the same picture but with different equations. So I prefer to keep it. So let's call it Korn type inequality. And if you like, you can attach this to remember or something, or refer to this one specifically. You can call it anisotropic if you like. Yeah, anisotropy. It's still not precise enough because some people will say anisotropic Korn inequality. They may think about an anisotropic an elastic medium whose coefficients C are anisotropic. Here the word anisotropic refers to something else. It refers to the fact that the geometry is anisotropic. The body is much longer this way than that way. But okay, I will stop here. I will not make it more specific. Just refer to this as an isotropic Korn type inequality. And this is the inequality. So that under the notation on the right, so under the notation or coordinate system, under the choice of coordinate system, here we get this bound. I'll write it in this form because it's I shouldn't use C now. That's why C is not good. I need to use a different letter for this. M? What? M? No. Gamma. So, right. So I have, as I kind of already anticipated here, but I mean, it's a question. It's questionable that I anticipated here, because I anticipated this from what I get here, right? So this comes first, and then I realized that I need to scale the forces in different ways. So this is bounded by above by the quadratic form, well, corresponding to this bilinear form, which is when we put UH instead of phi, right? So C U dot E of U, right? This is omega H is the same. So this is it. So this is true. So this gamma does not depend on H. That's the key point, right? So gamma is H independent. Gamma is H independent. And this is true for all U in for all U in H1 on omega H squared, right? So two components. Subject to the condition, subject to this condition. So, yeah, well, actually, this, I mean, some people may disagree with the choice of this terminology, Courant type inequality, because Courant type for well, the Courant inequality for, we can argue that the Courant inequality is a relationship between the gradient of the function and its symmetric gradient. So then, strictly speaking, a Courant type inequality would have the symmetric gradient here, and bounded above or bounded below by the integral of the gradient of U squared or something like that. Well, but you know, this terminology is vague. So then I bound the L2 norm of U above by the norm of the gradient in L2, right? So it's a kind of combination of what some people would call a Courant inequality and the Poincaré inequality, if you like, which I still call a Courant inequality. But how do we prove this? I mean, this is the proof of this is non-trivial. You can no longer prove this by that spectral, you know, simple spectral analysis argument that we had in the scalar case. Remember how we proved the Poincaré inequality in the scalar case? We just noticed that the corresponding constant was the lowest eigenvalue of some operator, then just worked it out by separation of variables. So it was 2 pi squared in the case of the Neumann problem, and something large, the 2 pi squared times 1 plus 1 over h squared in the case of the Dirichlet problem. That was straightforward, but it won't work here. First of all, because you don't have separation of variables. Well, and second, because it's anisotropic. Well, you could say, okay, now I have kind of guessed. Someone told me that I should make this scaling. I'm gonna scale it back, call this W2, put it back in there, and consider the corresponding H-dependent operator, and look for its lowest eigenvalue. But the separation of variables won't work because it's a vector problem. So what do you do? So it's very non-trivial, actually, the proof of this. but it's true nevertheless. This is a bit easier, like this. Sometimes it comes in this version. But we really need this version here to do our analysis. Of course, this one implies that one. So sometimes you hear people say that this phrase said that the Poincaré, the constant in the Courant inequality for thin bodies behaves like 1 over h squared. What does it mean? It means that first they put this h here, And second, for them, the constant in the Corn inequality is this. This is what they're talking about, right? But okay, this is not enough for us. We want H here. So, and that's the key. That's the first key point in that analysis, right? In the first paper. So that's right. So I'll just write. I suggest that you look at that paper and you kind of maybe over the weekend even, if you're curious. It's accessible. You can I mean the material is fairly accessible. You can handle it from what we discussed now, and I'll just write the answer, okay? And the answer is something that shows also, of course, the fundamental difference between scalar and vector problems, and the new exciting features that we get. So this kind of this inequality gives us an appropriate compactness argument, right? And so here is the theorem. So okay, so okay, so the formulation is actually the theorem is formulated in these terms. So I'll write. So suppose that a bit more general. So the forces F1, the components of the force also depend on H. So and in this way, in such a way, okay. So in such a way that F1H converges weakly to F1. Okay, so I suppose that. So what it means is that if it doesn't depend on H, then this is trivially satisfied. This is just F1. Then okay, so the second component. Sorry, the second variable. So if the first component times this quantity, right, x2 over h, converges weakly to some function g. So when f1 is fixed, this means, I suppose, that g is 0. So the weakly converges to its mean. The mean is 0. The mean of this is going to be 0. Well, it depends. It depends if f1 is a function of x1 and x2. Then it's going to be the mean of that function times x2 over h. But if it's x2 independent, then this is going to be 0. Okay, so f2h converges weakly to f2, which is trivially satisfied when f2 is constant, does not depend on h. So then u1h converges to weakly to u1, and u2h converges to u2, where u1 and u2 satisfy different equations, and different, not only with different coefficients, but of different nature. So, by the way, from what we have just discussed, what do you expect u1? What sort of equations do you expect u1 and u2 to satisfy? Using this kind of intuitive expectation that you need that u1, which represents the displacement in this direction, should be the displacement that you get when you pull things like this, pull this sheet of paper like this. So it behaves a little bit like a membrane, right? If you like, it is a membrane, and u2 corresponds. It describes what happens when you do this. and this is not a membrane. This is something else. Oh, any guesses? What? So have you heard about a plate equation, a biharmonic equation? The biharmonic. Where does biharmonic equation comes from? It comes from this fact that when you have a sheet of paper, then in order to describe, well, for small displacements, as I said, if they are large, none of this is applicable. It has to. You have to look at the finite equations of finite elasticity. You cannot use linearized elasticity. But if it's just doing something like this, then approximately you can use equations of linearized elasticity, and then such equations in the limit of a very thin plate give you the biharmonic equation, which is an equation of fourth order. So you already kind of know, you are pretty sure at this point that U1 is going to satisfy an equation of second order, a membrane equation, the equation of a drum. And the U2 is going to satisfy an equation of fourth order. So this is something that, well, I find very exciting personally. So U1 satisfies the problem. This problem, well, this condition because we attached our rod at one end, right? So this is the equation that we had yesterday. The weak formulation. We called it we referred to it as the diffusion equation, but as I said, you know, in elasticity you also have something like this, in an appropriate polarization, in antiplane shear. So you can continue calling it diffusion equation. It doesn't matter. It's just terminology, right? So just convention. So for all phi in H1, with this condition, and second, the limiting component for this satisfies a weak formulation of a problem of fourth order. So U2, and also it has higher regularity. That's another thing. That the geometry through the analysis of the problem, this feature of the geometry that you have a very thin body, gives you increased regularity of a solution. So this is the thing that features commonly in problems for thin bodies. So it's an H2 function. And if you have regular data, it becomes even more regular, right? It actually has a regularity H4, whereas this at best has regularity H2. If yeah, it will actually for this domain, it will be H2, and if F is in L2, but here the function will actually eventually be in H4. And it satisfies this weak formulation. This is curious to work this out. 1/3, just some kind of constant that pops up here. So in the analysis, just a second, I missed something. I need a letter for this. It's not a diffusion equation with the same coefficient as in the scalar case. It has an extra coefficient. Gamma, I don't know what to call it now. They call it rho in the paper. Not to be confused with the density rho, right? So I'll call it alpha. So it's a constant, so I can put it outside the integral. So, and here I have alpha as well. Alpha over 3. F2 psi and psi here are taken from this class, right? With an extra condition, of course, because it's one order higher. In different dimensions, yeah, I guess, yeah, but yeah. I don't know what. No, 3 is not the dimension, but yeah, but yeah. If you ask me what the equations of elasticity in arbitrary number of dimensions, that's gonna be a challenge for me. But yeah, it comes. Yeah, I mean that. Yeah, it's gonna depend on. Well, no. Well, I mean it comes from. I mean, it's the same sort of constant as 2 in the expression lambda plus 2 mu. Where does 2 come from? So, yeah. Yeah, okay. Okay, yeah. So, okay, so what you are saying, okay. What you are saying is actually challenging me because I have never thought about it this way. How it depends on the right. So uh-huh. Yeah. So and this alpha is the inverse of this tensor. Now, an interesting thing is how to define the inverse. That's your homework, part of your homework. You know, think about how you define the inverse of a tensor. It's a fourth order tensor, not a matrix, right? But once you think about it in certain terms, it becomes straightforward, right? So where this eta, I'm using the notation. So this eta is this matrix, where Tor is the tangent to the rod. Okay, so Tor is the tangent to the rod, so it's a more general expression than in relation to our picture. So in our case, Tor is just going to be E1. But if your rod was like this, they just want a more general form because they will be looking at nets eventually, where you have this shouldn't use the word rod, the net components, right? Strips. They go in all sorts of directions. So when the tangent is Tor, you need to calculate the Tor inner product, outer product rather. So or this sometimes people write. So it's a matrix, right? And this is the constant. So for example, for the homogeneous and isotropic and homogeneous case. So where we have lambda and mu, remember the Lemma parameters. This rho, they call it rho. So alpha. Alpha is rho mu. It's 4 mu lambda plus mu. Lambda plus 2 mu. So I mean, I might be wrong, but this 3, it's has the same nature as this 4 or 2. But okay. So okay. So well, I guess these equations are worth looking at maybe for a few minutes. But this is so you can see that the two components behave essentially in very different ways. Now, okay. So given the discussion that we had about the scalar situation of these strips with some diffusion-like process on them. Diffusion-like, yes, diffusion-like setup rather. In the limit as h goes to 0, we get this singular structure with the diffusion equation along each edge, and with some conditions we saw over there at each vertex. Once you consider the situation with more than with more than one rod linked somehow together, with more than one, when you consider a net, well, you also have the challenge of studying the asymptotic behavior around this point of junction between the strips, and working out what the conditions, joining conditions, are going to be there. So you know from here that from this equation you're going to have two constants to determine on each edge. From this equation you're going to have 4 more constants. So going from a scalar problem to 2D elasticity results in moving from two arbitrary constants here to as many as 6 to determine on each edge. 2 plus 4, right? And so, and of course, when you do the complete analysis, you end up with the number of conditions at the vertices that matches exactly the number of constants that you need to find. And I'm not going to write those conditions. They are written in the paper. right. But well, you can interpret them in elasticity in the way that tells you how those vertices behave, how they're displaced. Okay. So okay, so I was hoping to talk about the measure theoretic approach to singular structures today as well, and even in addition, my plan was to discuss the formulation that is referred to as the sort of quantum graph formulation for a singular structure. But I think I've run out of time for now. So I'm running a bit behind with my lecture course. Yeah, it's well. Yeah, but it's a quantum graph. Well, basically, the quantum graph is something that you see here. Yeah. So I have partially ticked that box off, but the measure theoretic formulation is something different. So the measure theoretic formulation for for singular structures. So if you think about this limiting geometry, then I can try to forget about what I've done. Just look at this geometry and try to write down the governing equations, like the equations of elasticity or the diffusion equation, on this system as if it was, well, looking at it as embedded into the Euclidean space. Right? I can look at it as a one-dimensional structure, so going along each of the edges and solving ordinary differential equations along each edge. That's the quantum graph approach. But also I could look at it alternatively as a structure that is embedded in the Euclidean space and write a partial differential formulation. But I would have to replace the Lebesgue measure by something else. By what? By a measure that for each domain measures the total length of the components of my singular structure that that is part of that domain, right? That are part of that domain. So this length plus that length plus this length. So that's a measure, right? It's a singular measure. It's not absolutely continuous with respect to the Lebesgue measure. So Lebesgue measure sets of Lebesgue measure 0. This segment, for example, its Lebesgue measure is 0. As a non-zero measure with respect to the new measure. The new measure tells me that it's the length of the segment. So I have to, if I wanted to use, if I wanted to write partial differential formulations, still using partial differential equations, I would have to start using singular measures. I have no other choice. And that approach features a lot, is quite interesting. It actually, you now have to, it's interesting in that you have to work out the difference in the behavior of the displacements, again, in the direction along which the measure looks like Lebesgue measure. So along this direction, it looks like just a Lebesgue measure on the segment. And in the directions orthogonal or transversal to these links, where some theory needs to be developed in order to describe what that partial differential equation means there. So, and it turns out that you have to use a new, a more general kind of Sobolev space. Have you heard about Sobolev spaces? No? Well, some of you, yeah. So, I don't know. Actually, Sobolev spaces have featured in my presentation. I don't know. Now I'm I'm a little bit uneasy. So maybe I should have written what this is. Well, so yeah. Well, better late than never. Yeah. So, but yeah, for those who do know, who are familiar with Sobolev spaces, here you have you deal with Sobolev spaces where a function can have many gradients. So you will ask, how can this be? Well, it can be in mathematics if you put in place an appropriate framework. So and that precisely accounts for the fact that you have this degree of freedom in that direction, in the direction orthogonal to this to the rods. So arbitrary displacements in those directions give you the components of the gradients of 0. So believe it or not, 0 has many gradients, not just 0. Right. So I think on this note I will finish for today. So, and now we have another break, right? Just a 10-minute break.